let bindings look like this. Let x equals 5, semicolon, x plus x. What this is really saying is let x equals 5 in the expression x plus x. And so you could use it with something else by surrounding it with curly braces, like so. And times it by let y equals 4 minus 6, semicolon, y divided by y. Reason uses curly braces and semicolons instead of parentheses and the words in or in the expression, because JavaScript programmers are used to that. The curly braces also enforce scope, which means you can't use the x or y outside of them. In Reason, curly braces and parentheses are basically the same, unless you're using tuples and records, in which case the rule is parentheses for tuples and curly braces for records. The syntax tree in this case looks like this. A star at the top. On the left, we have a let, which has 3 parts. The binding identifier, x. The expression it's assigned, the number 5. And then a plus, followed by 2 x's on either side of it, for where the expression is used. Similarly, on the right, we have let y for the identifier. The expression is a minus of 4 and 6, and where it's used is a divide for y over y. When a computer sees this, it takes these steps to figure out the end result. First, it substitutes x in the expression x plus x, so we get 5 plus 5 times the rest. Then it reduces it by adding 5 and 5 to get 10 times the rest. Now 10's a number on its own, and we know we have to multiply by an integer on the right, so we have to reduce the thing on the right. We reduce 4 minus 6 to negative 2. Then we substitute y equals negative 2 in y divided by y. Then we simplify negative 2 divided by negative 2 into 1. And then finally, 10 times 1 reduces to 10. This isn't the only way of doing this. We could have reduced it so it was the right side before the left. Or substitute before reducing like this, where we say let y equals 4 minus 6 reduces to 4 minus 6 over 4 minus 6. Note that let x equals 5, semicolon, let y equals 10, semicolon, x plus 5 times y is really the same as nesting it inside the tree. So let x equals 5, then the expression that it's used in is let y equals 10, and then the expression on the right again would be x plus 5 times y. In fact, when the computer tries to understand your program, it converts this kind of flat form that's easy to read for humans into this nested form that's easy to break down into smaller and smaller chunks for the computer. Pause the video and try writing out this expression in a syntax tree as a nested form. We can even do what's called an if expression. If x is greater than 5, the string hello, else the string goodbye, double plus, world. So if x is greater than 5, we have hello world, and otherwise goodbye world. The syntax tree of this looks similar to the let expression. We have the double plus and the world on the right, and on the left we have 3 parts to if. The first is the condition, which involves a greater than, with an x on the left and a 5 on the right. The true branch is the string hello, and the false branch is a string goodbye. And if we want, we can have even more than one thing using tuples. So we can have a tuple consisting of hello in the first position, 5 plus 5 in the second, and something more complicated like let temp equals 5 times 6 in let temp2 equals temp times temp in temp plus temp2 over 3. We could even try to come up with our own little syntax rules for a reason program. So we can say an expression is let a name equal expression, semicolon expression, or if parentheses simple expression, another simple expression, else a simple expression, an expression op another expression, or a simple expression. A simple expression can be something that has only one part, like an integer literal, int, a string, a float, a boolean, a list, a tuple, a record, or name, or a more complicated expression, but surrounded by either curly braces or by parentheses. An operator op could be any one of the ones we've seen, such as plus, minus, times, divide, plus dot, minus dot, times dot, and divides dot, the double bar for or, the double ampersand for and, less than or equal to, greater than or equal to, double equals, not equals, exclamation mark, and the double plus. A list can also be part of the rules for the syntax. We could say a list is either empty, with just the 2 square brackets, or it's got a bunch of list items inside of it. Whereas a list items is either just an expression on its own, or it's an expression followed by a bunch more list items. We can have a similar rule for tuples as well, where we replace the square brackets with parentheses. Try coming up with a rule for records. But remember that records need the type declaration first. And from before, a bunch of expressions can either just be a single expression, or it can be an expression followed by another bunch of expressions with a semicolon in between them. I encourage you to have a look at this link and try making some expressions using the rules I've shown you. Try typing it, or even better, do it on paper. But don't worry about whether or not it makes sense as a program. The point here is that you get familiar with syntactic constructs as just syntax trees that you can make and manipulate however you want. We'll see next time that types are a good way of making sure that the programs that you write actually make sense. And I'd like to point out that learning a full grammar is not typically how you learn a language as a beginner, but they're really good for reference, and once you get used to it, it's a really quick way of learning the language's syntax. The point here is to look at simple examples and seeing how they generalize. I am fairly sure that the grammar that I've shown you has flaws in it and doesn't reflect reason accurately, but it's a start, and this is exactly how people figure out what a language should look like. They write something simple and then they figure out where it works, where it doesn't, and they fix it accordingly. The rules that we've looked at and the way we've described them is typically called Backus-Naur form, and a lot of languages are specified this way using what's called a context-free grammar. You can see some more examples in the links for popular languages such as C, Python, OCaml, Reason itself, and Haskell. You can also see Rosetta Code, which is a great website for seeing that how similar or different programming languages are in their approach to syntax for solving the same problems, and even an interesting post about why Haskell is not context-free,